Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 2.3 on families of functions, also known as transformations of functions. So there are certain things that we can do to a function that always affects its graph in the exact same ways, no matter what the base function that we're dealing with are. So if we have some base function of the form y is equal to f of x, the three things that we can do is we can multiply it by an a out front, we can add or subtract a constant at the end outside of it, or we can add or subtract a constant inside with the x, which has the effect of function evaluation. You replace x with x minus h. Now, all of these are going to be real numbers, so they're letters for right now, but these are just stand-ins. These will be numbers. And a, the thing out front, can't be 0, because if you multiply the function by 0, it all goes away, and you just get a horizontal line on the y-axis. Y is equal to 0. That's not very interesting. So there are two major parts to this section then. The first is you have to know what your base function's graph looks like. And that's the reason why we spent a lot of time graphing in the previous section, because we're going to be bringing forward the three types of functions we looked at in section 2.2. And then you have to know what effect each of these letters has on the graph. And so that's what we're going to be taking a look at here in section 2.3. So with that said, let's do a quick review of the base graphs that we first introduced in section 2.2. So we've got three functions in total that are going to be our base graphs that we're performing transformations on here. That's y is equal to x squared, our base parabola. It's got vertex at the origin, it opens upwards, and there are going to be three ordered pairs that you want to track. 0, 0, the origin, the vertex, positive 1, 1 to the right, 1 up, and negative 1, positive 1 to the left, 1 up. That triangle of points we will be tracking when we transform the graph with those three letters. The second graph has y is equal to absolute value of x. That's just that V shape going off in both directions. Same three ordered pairs that we have for y is equal to x squared. Same triangle, 0, 0, 1, 1, negative 1, 1. The only difference is that the shape you connect through them is different. Right? For x squared, you've got that rounded u, whereas for absolute value of x, you have that straight line going off in both directions. And then last but not least, our final base graph we're going to look at in this section, y is equal to square root of x. In its base form is the top half of a sideways parabola. And the key points of this, and again, the x values are the thing that make the inside of the square root nice, that's how you remember it, are 0, 0, 1, 1, and 4, 2. Because if you plug in 4 for x, square root of 4 would be 2. All right, so now that we've taken a look at these three base graphs again, let's start introducing what each effect those three letters has on our base graphs. So the first letter that we're going to take a look at is the one that is tangled up inside of the function with x, the h. And so if h is positive, then the graph of y is equal to f of x minus h, minus sign built into the formula, that's going to be important, is the graph of just the base graph f of x translated or shifted h units to the right. So it pushes it to the right. Now, h is on probably the trickiest of the three variables, and that's because it always does the opposite effect of what you see in parentheses, much like when we were talking about the center of a circle back in section 1.1, where when we were looking at those, the x value of the center of the circle was always the opposite sign you see in parentheses. In other words, this was pretty much the same transformation happening, even though this isn't a function. This x minus h shifted the center of the circle to the right h units. Now to take a look at what that would appear as, with the three base functions we're looking at in this section, remember this is basically function evaluation. You're replacing x with x minus h. So if your base function is y is equal to x squared, our parabola, you would replace that x with parentheses and then plug in x minus h. So it's x minus h quantity squared. For y is equal to absolute value of x, you replace the x inside of the absolute value with x minus h. That should not be squared anymore. All right, it's just a copy-paste error from the previous one. And for the square root function, square root of x, you replace the x inside of the square root with x minus h. So the easy way to tell if you're dealing with a horizontal translation, a shift left or right, is that it's always tangled up inside with the x. To show you an example of one of these horizontal translations in action, the red graph here is our base graph of y is equal to x squared. The blue graph is the graph of y is equal to x minus 3 quantity squared. So although that you see it as x minus 3 in the parentheses, that has the effect of shifting the graph to the right 3 units. All right, and that's how we would describe it. You would say shifts or translates right 3 units. Or even just shifts right 3 would be okay. And you notice that's what happened to every single ordered pair. The y values didn't change. The y values are still the same for all 3 ordered pairs. But for the x values, 3 got added to each. So this -1 went 3 to the right to positive 2. This positive 1 went 3 to the right to 4. And this 0 went 3 to the right to positive 3. So each ordered pair went exactly 3 units to the right. To expand on that, if you see addition inside of the function, then in that case it moves it to the left h units. So again, it's always the opposite direction of what you would expect from the sign in parentheses. If it's a plus, it goes in the negative direction to the left. If it's a minus, it goes in the positive direction to the right. And so to illustrate this example, if you have our base graph of y is equal to square root of x is the red graph here, then the square root of x plus 2, you would know that this is a shift left or right because the plus 2 is inside the square root with the x, right? Tangled up with the x. And because it's a plus 2, everything gets moved to the left in the negative direction. So 0, 0 gets moved 2 to the left, 1, 1 gets moved 2 to the left, and 4, 2 gets moved 2 to the left. Now at first glance, these shapes might look like they have a slightly different shape, but that's only because you can see more of the green graph in this case. If you compare it box for box, you would see that these two graphs have exactly the same size and shape. The only difference, everything is just moved 2 to the left. All right, so if the h on the inside of the function is added or subtracted to the x value, so it shifts the graph left or right, then the k on the outside is added or subtracted to the original f of x. This is added or subtracted to the y values. And this one is much more straightforward because there is no flip sign. It's a plus in the transformation formula. So if you have a plus k on the outside, the whole graph gets shifted k units up in the positive y direction. And if you have a minus k on the outside, you're subtracting from the y values, the whole thing gets shifted k units down in the negative y direction. All right, so all that's happening here is you are adding or subtracting k to all of your y values. right? So to distinguish this from the h's that we saw earlier, to know how you can tell which is which, this is outside of the original function, not tangled up with the x. So if you take a look at the transformations of our base graphs, while for h, we had x minus h quantity squared, for the k, you still have the base graph of x squared, you just get this plus k tagged on at the end. So it's outside of the exponent this time. For the absolute value, while before we had x minus h inside the absolute value, the k is outside of the absolute value. And I changed up the sign just to give an example of both. All right, and then same for the square root. For the h, the horizontal translation, that was inside of the square root with the x. For the vertical translation, the shift up or down, the k is outside of the absolute values, separate. All right, so for some examples of vertical translations, once again, the red graph is our base graph, square root of x, with those same three ordered pairs, 0, 0, 1, 1, and 4, 2. If we were to graph square root of x plus 2, where the plus 2 is on the outside, you just add 2 to all of your y values. We would say that this shifts 2 up. All right, so every ordered pair just goes up 2 units. If we had y is equal to absolute value of x as our base graph, so the red graph at the top is our base graph, and then we wanted to graph y is equal to absolute value of x minus 3. This minus 3 on the outside, we would say, shifts the graph down 3 in the negative direction. So every ordered pair, the entire graph would just go down 3 units. Let's take a look at our final letter now, and this one can actually serve a couple of different purposes, but the idea is always the same. So what you're doing is you're taking your original y values, f of x, and you are multiplying them by this coefficient of a. It's the act of that multiplication which can have a couple of different consequences. So to show you what these transformations would look like, again with our base graphs, you would have a times x squared, so it's just a coefficient out front. You would have a times the absolute value of x, or you would have a times the square root of x. All just multiplication. Now, to begin with, we're going to look at the specific case where a is equal to negative 1. So in this specific case, it would be negative 1 times x squared, negative absolute value of x, and negative square root of x. Well, think about what would happen. If you took all of your y values and you multiplied them by negative 1, they would have the same magnitude, just a different sign. So a y value of positive 1 would flip and become a y value of negative 1. And so what effect that has is it takes your graph and it reflects it vertically. It gets mirrored across the x-axis. So again, our red graph here is our base graph of y is equal to x squared. This purple graph is the graph of negative x squared, so an a of negative 1. It has the exact same size and shape. The only difference is it gets reflected vertically. So instead of opening upwards, it's now opening downwards. And you'll notice that points on the x-axis themselves don't get affected at all. This point 0, 0 is shared between both graphs, because if you take a y value of 0 and you multiply it by negative 1, it's still 0. The other effect that a can have on the graph is stretching or shrinking the graph vertically. And again, it's still the same idea of multiplying your y values by a. So think about it. If you had y is equal to 2 times some original function f of x, you're taking all of your y values and you're doubling them. So they get twice as tall, either in the positive direction if they were already positive, or in the negative direction if they were already negative. And so in that case, we would say that your graph would be stretched vertically by a factor of 2, by a factor of a, whatever the number out front is. Everything gets twice as tall. On the other hand, and this, by the way, would happen anytime your a is greater than 1. So if you had y is equal to 3f of x, everything gets 3 times as tall. We would say that the graph is stretched vertically by a factor of 3. On the other hand, let's say you had y is equal to 1/2 f of x. This time you're taking all of your y values and you're multiplying them by 1/2. Say they all get half as tall. In this case, we would say that the graph shrinks vertically by a factor of 1/2, still by a factor of whatever the number out front is. And this will happen anytime you have an a between 0 and 1. You're multiplying by a number smaller than 1, so all of your y values shrink in size. To get some examples, once again, we've got our red graph, y is equal to x squared is our base, and then the purple graph pictured here is y is equal to 3x squared. So this is a graph that's been stretched vertically by a factor of 3. And so you're not adding or subtracting this time, you're multiplying, right? Multiplying. So this y value of positive 1 over here gets multiplied by 3. It becomes 3 times as tall. So it's now a y value of 3. This y value of positive 1 also gets multiplied by 3. And this y value of 0 also gets multiplied by 3, which still leaves it at 0. So that doesn't really have much of an effect. But think of it kind of like a rubber band, where you have a rubber band that has a little bit of slack in it. That's this red graph. And then when you stretch it vertically, you're pulling at the top of the rubber band, everything gets stretched upwards. That has the side effect of also making the graph look narrower. But that's not what's happening here, although it can be pictured that way. This is everything getting stretched vertically, 3 times as tall. And for the shrinking example, if we have our base graph of y is equal to absolute value of x here, and I wanted to graph 1/2 times the absolute value of x, which I wrote as 0.5 in this case, 0.5 is 1/2, then all of your y values get twice as big, or excuse me, half as big. So this y value of 1 now goes down to 1/2. Same over here. And so everything gets half as tall. So now this red graph is being shrunk vertically by a factor of 1/2. Imagine that you set something heavy on top of it, and now it's just being compressed downwards. So we've mentioned then that A can have 2 effects. It can reflect the graph vertically if it's -1, and it can stretch or shrink the graph vertically if it's something other than 1. But you can actually combine these two together. So for example, if you have an A of -2, it combines these two ideas together. It will reflect the graph vertically, but also stretch it by a factor of 2. But again, the idea just goes back to you're multiplying all your y values by -2. So if you have a y value of 0, if you multiply it by -2, it's still 0. If you have a y value of positive 1, if you multiply it by -2, it's now -2. And if you have a y value of positive 2, if you multiply it by -2, it's now at -4. Right? And so this is a graph that has been both flipped vertically, which would have put it right here, but then also stretched vertically. The thing is not only can these transformations happen one at a time, but you can also have all 3 happening at the same time, interacting with each other. And for the most part, you can still just handle the transformations one at a time. There is something important with the order though, if you do. And that is that it's always important to stretch or shrink vertically before you shift vertically. And if you have trouble remembering that, just keep in mind the order of operations. The shifting that we do up, down, left, and right is addition and subtraction, whereas the stretching, shrinking, and reflecting that we do is multiplication. So just like in the order of operations, the multiplication comes first, and then the shifting, the adding and subtracting, comes second. You can also think of the transformations as just tracking the ordered pairs themselves, although I don't recommend this method necessarily. But this does do a good job again of describing what each letter does. So keep this in mind. The H shifts the graph left or right H units, but because of the minus sign in parentheses, it's always the opposite direction you would expect. So when you go from x to x plus h, that h is the opposite of the one that you see in parentheses. So if you had x minus 2 quantity squared, you would add 2 to all of your x values. And then for your y values, that's what the other two letters affect. You multiply by a, and then you shift it up or down. You add k. So with that said, let's take a look at some examples involving transformations. All right, so in example 1, we're asked to use transformations to graph the following function. And we've got y is equal to x plus 5 quantity squared minus 4. So first things first, this is a transformation of the base graph of y is equal to x squared. So a transformation of x squared would look like this. So the x minus h replaces the x in parentheses, the a is multiplied out front, the k is added on at the end. And so first thing you might notice is that there is no a in this case. It's implied to be 1 times, so it's not having any effect. So that's one less transformation we've got to worry about. Now, what I want us to be able to do from this section is to not only be able to graph the transformation, but be able to describe it in words. And so in this case, we have two transformations taking place because of the two letters that still exist. From the plus 5 in parentheses, this graph is going to get shifted left 5 units, opposite direction of the sign you see in parentheses. So because of the plus 5, it's moving to the left. And because of the minus 4 on the outside, this graph, our base graph, shifts down 4 units. All right? Again, the sign on the outside explains exactly what it's going to do. It's only the one tangled up with the x that gets a little bit confusing. All right, so if we're going to graph these transformations, we have to know our starting place. That's why it's important to know your base graphs in this section. So our base graphs for y is equal to x squared have 3 ordered pairs. The origin, one to the right, one up, one to the left, one up. Connect the dots with that parabola shape. And you've got two options here. The first is you could actually do both transformations at the same time. With a little bit of practice, it's not that difficult. Or you could graph them one at a time. In this case, the order also doesn't matter because we don't have an a out front. If there was an a, we would do that first, do the multiplication first. But since there's not, the order doesn't matter. So I'm going to do the transformation in 2 steps just to show you exactly what's happening. So why don't I start with the shift left 5 units. All right, so all 3 of my ordered pairs are going to move 5 to the left. So the origin's the easiest to track. It's currently at an x of 0. So if it moves 5 to the left, it would be at negative 5. I'm not changing the y values yet. I'll do that in a second. This ordered pair over here has an x of negative 1. So if it moves 5 to the left, it would now be at -6. And our final ordered pair has an x of +1, so if it moves 5 to the left, it would end up at -4. You end up with the same triangle of dots, which is what we expect in this case. All right, same graph, just move 5 to the left. This would be what the graph of just y is equal to x plus 5 quantity squared would look like, without the -4 at the end, because I haven't done that yet. And so now, to finish the problem off, I'm going to take that red graph and apply the second transformation. I'm going to shift it down 4 units. All right, so my x values are still going to be the same. It's just my y's that are changing this time. So if I start at the one that has a y value of 0, if I subtract 4 from that, I move it 4 down, it would now be down at a y of -4. The other two are both at a y of +1. So if I move those down 4, that would put them at a y of -3. Again, same triangle of dots. That's what we expect every time. And so our final graph of y is equal to x plus 5 quantity squared minus 4 would look something like this. All right, so let's take a look at another. And we're going to look at one of each type, so 3 examples in total. And for this one, we've got y is equal to 4 minus 2 square root of x plus 1. First things first, the order is not quite what we expect here. So a transformation of the base graph of square root of x, in general, the x minus h would go on the inside of the square root, the a would be multiplied out front, and the k would be added on at the end. The only thing that's happened is that they've swapped the order of the two terms. So if I want this to line up a little bit better, I can write this instead as -2 square root of x plus 1 plus 4, because the 4 is positive and the second term is negative. Those signs carry down because I'm not moving anything across equal signs. I'm just swapping the order of the two terms. And so this time we've got all 3 letters in play, which is actually going to have 4 effects on the graph because A potentially has 2 effects by itself. So let's describe what's happening. First things first, because the A out front is negative, this graph is going to be reflected vertically. The other effect from A being -2 is that the graph is getting stretched vertically by a factor of 2. And truth be told, both of these transformations will take place at the same time. We're not going to picture those individually because, again, we're basically just going to multiply all of our y values by -2 and call it a day. But these are the 2 effects that are taking place. Because of the +1 inside of the square root, this graph is also going to shift left 1 unit. And because of the +4 on the outside, the graph is going to shift up 4 units. All right, so those are the transformations that are taking place with this particular graph. So let's get a good picture of it. So this is a transformation of square root of x. We need our base graph. And again, if you ever forget your x values for this, it's the perfect squares, the one that make the inside of the square root nice, 0, 1, and 4. Square root of 0 is 0. Square root of 1 is 1. And square root of 4 is 2. Right, so that's the top half of our sideways parabola. Now, order is a lot more important this time. Because a does exist, we want to do the multiplication first. So what I'm going to do is I'm going to take my y values and I'm going to multiply them by -2. So my y value of 0 is still going to be 0. My x values are not going to be changing in this step. My y value of +1, if we multiply that by -2, would put us down at -2. And if we take our y of +2, we're down at -4, and so we end up with a shape that, a bit stretched out, looks like this. It would level out if we had a little bit more spaced graph. All right, so this would be a picture of the graph of -2 square root of x, because the -2 is the only transformation we've done so far. And this is actually the purple graph that we showed a few slides ago. Now, again, you could do the next two individually. I'm actually going to combine these together and do them in one step. So I'm going to take each of these ordered pairs, I'm going to move them 1 to the left and 4 up. So starting with my ordered pair here at the origin, I'm going to move that 1 to the left and 4 up, which would put us at -1, +4. My second ordered pair here is currently at an x of 1. So if I move it 1 to the left, it would be at an x of 0. And it's currently at a y of -2. So if I move it 4 up, -2 plus 4 would put us at a y of +2. And then last but not least, our point down here, which is the ordered pair 4, -4. If I move it 1 to the left, instead of an x of 4, it's going to have an x of 3. And if I move it 4 up, instead of a y of -4, it's going to be at a y of 0. Right? So again, if you try to do a lot in one step, maybe it's helpful to write out the ordered pairs and picture what effect that's having on your x and y value, and then you can just plot the transform point. And so it's the same shape that we have here, it's just been moved left and up. So we end up with a graph that looks like this. All right, so let's take a look at one more. And this one, I'll track the ordered pairs a little bit closer so that we get a better idea of what's going on exactly. And this one is going to be a transformation of our base graph of absolute value of x. So we might as well go ahead and write out the starting point for that, and then we'll talk about transformations. So our three ordered pairs are 0, 0, 1, 1, -1, 1, straight line in both directions. So now let's talk about what's actually happening. All three letters are present again, much like in the last one. Let's start with the two out front, because that's what we would do first in the transformation order anyway. So it's a +2 this time around, which means the graph is not getting reflected. So all that's happening this time around is that the graph is being stretched vertically by a factor of 2. All right, from the -1 on the inside, it's tangled up with the x. It affects our x values, left and right. This one is going to get shifted right 1 unit. Opposite sign of what you see in parentheses. Because it's an x -1, it gets shifted +1 in the x direction. And then last but not least, from our +1 on the outside, our k, this is going to shift the graph up 1 unit, +1 to all of the y values. All right, so once again, I'm going to do this in 2 steps, one for the stretching, and then 1 step for the shifting. All right, so starting with the 2 times the absolute value of x, we're going to take all of our y values and double them, multiply them by 2. So if we multiply 0 by 2, that would still be in the same location. That doesn't change. For our second ordered pair, if we multiply this y value of 1 by 2, it gets stretched up twice as tall to the point 1, 2. And same thing on the other side. If we multiply this 1 by 2, it gets stretched up twice as tall. And so our shape now looks still a straight line in both directions, like this. It's just a steeper line in both directions now. Now let's talk about the shifting. So we're going to take all of these ordered pairs, we're going to move them 1 to the left, 1 up. All right, so let's start with the vertex again. It's currently 0, 0. We're going to move it 1 to the left, 1 up. So we're going to subtract 1 from the x, add 1 to the y. For the point -1, 2, if we move that 1 to the left, that's going to put us at an x of -2. And if we move it 1 up, instead of being at a y value of 2, it'll be at a y value of 3. And last but not least, for the ordered pair +1, 2, if we move it 1 to the left, that's going to put us at an x value of 0. And if we move it 1 up, that would also put it at a y value of 3. And again, your x squared and your absolute value of x will always maintain that symmetry when they're being shifted around. So if this ended up at a different y value than this one, I would know I did something wrong. All right, and so now I'm just going to connect the dots with the V shape. And that is the red graph here moved 1 to the left and 1 up. And so this would be the graph of 2 absolute value of x minus 1 plus 1. Now it occurs to me that I haven't been stating the domain and ranges of the functions we've done so far. So let's make sure we hit that up with this one. So again, it's just an extension of what we were talking about in the previous section 2.2. Read the graph, project the graph onto the x values and the y values. So the domain, left to right for x, so this goes forever to the left, forever to the right. Like all absolute value functions, the domain is all real numbers. The range in this case, lowest y value to highest, the lowest y value is +1, and it goes forever up to positive infinity. And that is it for section 2.3, families of functions. So again, you can kind of break this section down into two core ideas. The first is that you have to know your base graphs. Y is equal to x squared, absolute value of x, and square root of x. And then the other more major portion is you have to know the transformations. So given a transformation of the form y is equal to a times the original function evaluated at x minus h all plus k, you have to know what each of these three transformations do, be able to describe them in words, and be able to graph a transformation. So basically everything we did in the last three examples is what you're expected to be able to do from this section, 2.3. As always, if you guys have any questions, please make sure you let me know, and I will see you in the next video.